Oh, yeah. Okay, today we're going to be starting right at the end of the mineral section, and we're about to get into rocks. But before we go there, I have called several times to the planetarium, left messages, but finally yesterday I was able to actually talk with somebody. And it was, I guess, a student worker or somebody like that. Said she couldn't give me a lot of information, but thought that maybe next Tuesday we could come. But then I got an email. That's what I was checking the emails. I've been trying to call her today to find out. Couldn't get anybody to answer the phone today. And I just checked the email, and they did send an email after I talked with her yesterday and said, no, next Tuesday's out. They're booked up solid till the end of the month. So, 22nd? 26, I'm sorry, at 2 o'clock. 26 at 2, that's a Tuesday, I believe, right?
Yes.
Okay. So it's a couple of weeks off, and we're already going to be close to wrapping up the term by then. So we'll be through all the, well, of course, we're already through the astronomy part, and we'll be through the geology part. We'll be into weather, and we may have 2 back-to-back field trips if we can work them in to do. So, because the class only goes till early in March, right? Something like the 6th?
Like the first week. I think the 5th is finals or something.
Okay, so we don't have much time, okay? So we'll see if this works out. The information they just sent I'd never received before, and it sounds like they're now making a charge to go. And if they are, I'm not sure we've got money set aside to do so. But we'll see. I'll need to talk with him because we've never been charged before, but I've never received this attachment on the email that I received this time. So it may be they're changing the rules there, and we may not be able to go. But if we do, it'll be the 26th, Tuesday the 26th at 2 o'clock, which means we'll be leaving here at 1:15. So we'll need to leave here. If the trip happens, we'll need to leave right before this time right now. We'll need to leave at 1:15 at class start time in order to get there by 2 o'clock. Now, you don't all have to ride. I'll try to see if I can arrange to get a van. I can't probably get the entire class in a van, but I can get several. So if anyone is more convenient for you to go straight to Sanford rather than come in here, that's fine. We'll meet there at 2 o'clock. If this goes, there's no guarantee it's going to work because they still haven't got us fully in place, but I need to really talk with the guy, Mr. Weigel. I have 2 hours tomorrow morning, but yesterday morning I had 2 hours and he wasn't in. It was, well, late in that 2 hour period, I did catch the gal, or maybe it was over lunch or something. I did catch her. I think she's a student that's helping there. And in the afternoon, I could catch nobody. So it sounds like, I don't know. They have pretty flexible hours, it sounds like there. So I don't know if I'll catch them or not. So anyway, no trip to the planetarium before the end of the month, if then. We'll see what happens by the end of the month. Okay, the 26th at 2 o'clock in the afternoon. Okay, so what's up for today? Well, we finished chapter 17. I think we'll have plenty of time to finish chapter 17. And I believe we'll get started in chapter 18, which flows very nicely to what we've been doing in 17. At 3:45, we'll stop and have the lab from 17, okay? And that will be, we're going to go to a computer lab. I don't know which one. If we can use the orientation classroom, that's my first choice. If not, I'm going to try the lab upstairs, one of the accounting labs. So one of those 2 places is probably where we're going to wind up going for the last 2 hours a day. We'll take a break right before 3:45, and I'll scope out and see if either of those classrooms are available. So we will be working on the computer. You can work in teams, groups, whatever you want to do, and we'll go from there. So where does that leave us? Then on Thursday, we will continue chapter 18. There is a chance we could finish 18 on Thursday in the first 2 hours. If we do, then we'll have the lab for chapter 18 for the second 2 hours, and then we'll have the test on chapter 17 the last 30 minutes on Thursday. Okay? Make sense? That's if we are able to finish 18, which I think maybe we should be able to do. So any questions on anything we've covered so far or how to do? Now, here's another thing. I'm probably preaching to the choir here. I think y'all have been getting your work in pretty well. I know most of you have. It's the people not here. I can't return the earlier labs until I get them all in, because I don't want the right answers floating around out there, and that would cheapen your grades because someone else might happen to see an answer that you got wrong and they get it right, and that makes your grade even lower seeming compared, and they didn't know this stuff weren't even here to begin with. So trying to get everybody get things in, so I'm mostly talking to people who may or may not ever listen to this, but try to get things caught up. That's both labs and tests. Again, this group has been really good about taking your tests. It's the people not here are behind on all the tests and all the labs. So please try to get those caught up. All right. Any questions before we get going? Okay, we're right at the end of minerals. And if you recall, minerals are formed basically in two different environments. One thing that's similar about the environments are they both liquids are changing to solids. The difference is some of these liquids are liquid rock, which are at incredibly high temperatures, and when they cool, we'll talk about this a little bit later, when they cool slowly, then some minerals will come out first, those that have the higher temperatures at which they precipitate, and then later others and others, and finally the lightest ones do. Okay? The other thing that happens if they form rather large crystals then. If they cool real quickly, then you get usually very small crystals, and of course if they're cooling quickly, there's not a lot of differentiation in time. Okay. These then are minerals that form at normal temperatures. Most of these are in water solution. Not molten rock, that would not be at normal temperature. Molten rock is at very, very high temperatures, generally very deep into the ground. Okay? So these would be at normal temperatures, even though they could be very low, very deep. These are formed at the Earth's surface in contact with oxygen, carbon dioxide, and water. Okay? Now, I don't know if you realize this, carbon dioxide, water, those form carbonates. That's carbon, oxygen, and the water, carbon dioxide and oxygen form carbonates. Sulfur materials with oxygen form sulfates. Any other materials with oxygen form oxides. Halides are other materials like your column 7 in the periodic table, those salts, and then sulfides are things that just sulfur combines with other things. Okay. Except for the oxides, these typically have low hardness and low specific gravities. Okay? And when they say lower hardness, that would be 1s, 2s, 3s on the hardness scale. Lower specific gravities meaning not as dense. Okay? The minerals formed at high temperatures. The oxides tend to be hard and higher specific gravity in general. Okay? So those are the last, I think that's the last slide on minerals. Any questions? Oh, one more. Altered minerals. Materials that are in their normal state tend to hang around that way. But then when you do other things to them, you can change the mineral structure, specifically the crystalline structure. Exposure to different environmental pressures, temperatures, and chemical solutions can change minerals into new ones. Pressure could alter the bonding that went on, so therefore alter some of those crystal structures, typically forming harder, more dense materials. Pressure. Temperature could go the other way. It could melt what was a mineral, and when it recondenses, it forms a new mineral. Okay? Chemical solutions can eat away at certain parts of a mineral and alter it that way. Maybe substitute new materials into it. So all three of those, environmental pressures, temperatures, or chemical solutions, can change minerals into new ones. Now, for the temperature part, these generally occur above 150 degrees Celsius. Well, that's hot, but it's not super, super hot. 100 degrees Celsius is boiling point of water. 150 degrees is pretty hot, but not super, super hot. But this could be anything above that. But look at these pressures. 2,000 atmospheres of pressure. Right now we have over us 1 atmosphere of pressure, approximately. Okay? That's 14.7 pounds of pressure for every square inch on our bodies. That's a fair amount of pressure. Why aren't we not crushed? That's a lot of weight on us, right? 14.7 pounds for every square inch on our body. That adds up to a lot of weight. Why aren't we crushed? Because our bodies are pushing out with actually greater pressure than that. That's why when you nick yourself, the blood flows out. It doesn't suck, it can get sucked in, okay? Because we are under pressure ourselves and pressurized, okay? But that's at 1 atmosphere of pressure. 2,000 atmosphere of pressure would be 2,000 times, let's just round it to 15. That would be 30,000 pounds for every square inch of our body. No, we couldn't withstand that. Well, neither can the minerals. If they're at that great a pressure, typically they're going to be changing their crystal structure and other features about them. So, and this is usually way deep in the earth to get that much pressure. Now here are some altered minerals. These are pretty lousy to say examples. Garnet. For those of you who follow birthstones, what's that, a purplish or is that a red? What is garnet? Anyone know? I don't either. Epidote or epidote, I don't know what that is. Talc. Talc is that really soft material. It undergoes pressures and gets changed pretty greatly. Graphite. What is graphite? Anyone know? Second?
Pencil lead.
Okay, it's in pencil lead, but it's mixed with kaolinite in that. But it's a black, basically thick soot in a fireplace or something like that, on a lampshade or something, where something's been burning. That's graphite. It's a slick material. Okay, this is Reggie, right? It's a two-dimensional crystal, very slick. Actually, graphite is sometimes used as a lubricant. It's that slick. Okay? Take that graphite, and by the way, it's pure carbon. Maybe a few impurities in it, but generally pure carbon. Take graphite and put it under usually temperatures far in excess of this, but great amounts of pressure for long periods of time, and guess what comes out of it? Possibly diamond, which is not black, it's clear. Same material, same element involved, carbon, but now graphite is changed from a two-dimensional slick crystal that you could use as a lubricant for one of the best abrasive you have, you know, the hardest material going. Whereas graphite is very soft and slick, diamond is very hard and rugged. Okay. Serpentine is one of the asbestos groups of materials that asbestos comes from. under great amounts of pressure, it can be altered as well. Okay, I think that's the last one. Nope, one more. Our ore minerals. Okay, the reason I'm saying this, in these slides are from an older edition. These particular ones are not showing up in the text much, but they may be, but they're in different portions of the text. Well, ore minerals are mineral deposits with economic value, but remember, minerals are all fairly pure materials, okay? Not really mixed with that much else. And that's why the minerals with our ores that have economic value, that's what people like to mine. Often found in veins. Now, I don't know if any of you drive the new Interstate 22 that goes to Memphis. That's going through a lot of reclaimed mining area. And there are certain of those areas you can almost see the coal veins in the rock that are beside the road, okay, forming the banks there. I'm guessing from the fact that it's still there that it wasn't very pure coal and it wasn't very good coal, so that they counted it not worth mining. But anyway, those are samples of those veins. The phosphate mining they did down in Central Florida, I was telling you about, they dig down, they find those veins of phosphates and try to excavate those. What these veins are thin, flat bodies of mineral material, fairly pure, not totally pure, but fairly pure, and you'll see usually either the sedimentation process, more likely the altering processes created those minerals in those layers like that. Okay? Many of these are left over from the crystallizing magma, liquid rock that crystallized out at a given temperature and maybe pressure too, and this mineral came out of solution all about the same time. And I say solution, not solution. Came out of liquid form and mineralized, solidified about the same time, and that's how you get the differentiation above and below. Or they could have been flushed away from in hot water solutions and then crystallized later. Here are some examples of some of these ore minerals. Pyrite is iron sulfide. I don't count this as a valuable mineral, but iron sulfide is fool's gold. It looks just like gold. It's fairly dense, but not as dense as gold is, but it's fairly denser than most other things, so it can easily be thought of as that. But think of iron. Iron is a black, dark mineral most of the time. When combined with sulfide, it becomes a bright golden color. Chalcopyrite is a sulfide of copper and iron, and that's chalcopyrite, not calcium. You might think of that as copper and iron pyrite. And I don't know if this is where they get some of the copper mining. I don't think so. I think that's mostly copper sulfate that they use for the copper mining. But again, these are concentrations of fairly valuable material that's either been solidified out of magma at a constant in a central location, and therefore you get the veins over there, or else it's been dissolved by hot water solutions and solidified somewhere else. Now we're through with minerals. Any questions on the minerals part? Did anyone need that last one up there a little longer? I don't know. Did I go too fast? Everybody okay? All right, now let's hit the other part of the chapter. I don't want to say half. I don't know if it's exactly half. But the name of the chapter is Rocks and Minerals. But we did minerals first, and now we're doing rocks. What are rocks? Aggregations, that means compilations compiled by one or more minerals and perhaps other materials. Ooh, other materials. What other materials could there be? We're going to see an example of a picture a little bit later on of a piece of limestone. Now, limestone, the main mineral in limestone is calcite, okay? Calcium carbonate. But you can have mixed with other things, For instance, calcium carbonate might, I said calcium carbonate, calcite is calcium carbonate, but other materials, perhaps seashells. Not a mineral, because that came from a living organism. But that can be in a rock, but it wouldn't be a mineral. Okay? So when it says perhaps other materials, not even other minerals. Okay? Minerals are physically combined to make rocks. Now what makes a mineral is a chemical combination. The bonding is there. It's a physical combination to make rocks. One mineral with another mineral with some non-mineral materials. That's what makes rocks. Most rocks, catch this is especially surface rocks, but most rocks are silicate minerals. Okay? Even down deep into the earth, you still find a lot of silicates. Now the iron is predominant down there, but you still find a fair amount of silicates. Now, rocks are formed and classified on how the rocks were formed. Okay, they're classified by how the rocks were formed. Three main groups. You may have subgroups of some of these and off groups, but three main groups. Igneous rocks, sedimentary rocks, and metamorphic rocks. Okay? Now we're going to talk about each one separately, so I'm not going to define them now. I'm going to let the future slides define them. So when y'all have this done, I will move on. I'll just introduce, to begin with, igneous. What word do you almost see in that? If you add a few more letters after IGN, second? Oh, did you say ignorant? No, that's not what I was talking about. Ignite. In other words, hot. Igneous rocks are all from hot rock. They were once magma. In fact, previously magma. They were melted rocks. Igneous rocks were immediately prior to being rocks, were molten, were melted. So that's where the name igneous comes from. The name sedimentary, they come from sediments, okay? Things coming out of solution, out of solution, out of solution, getting buried deeper and deeper, and at some point they become rocks, okay? I didn't say what the sediments were. We'll talk about that on the slides. Now, metamorphic rock. Does anyone know what metamorphosis is? Or an example of metamorphosis? The classic example is a little fuzzy, fat, ugly caterpillar going into a cocoon and coming out a butterfly or a moth. Okay? That's metamorphosis. Changing completely. Gavin's here. Okay. Now, another example of metamorphosis, this is not a real one, this was a fictional one, but by a metaphysical type thinker. Boy, I can't think of the author's name now. Pretty famous author. Weird, but he wrote a book in German, and it's I think the title is Metamorphosis, okay? But his story, his fictional story, was this really obnoxious character. And you got to meet him and see how obnoxious he was for the first part of the book. And then one morning he woke up and he was now a cockroach, okay? And that was his metamorphosis. So he had to learn to live as a cockroach, which he had been acting a lot like as a human. And supposedly, that's the story. Going blank on the author's name now. But we'll talk about that too. So let's start with igneous rocks. All igneous rocks were formed from magma. Okay. Molten rock. Now some of these were formed above are on the Earth's surface and some below the Earth's surface. Now, second, here's a statement. All the other rocks, sedimentary rocks and metamorphic rocks, were at one time igneous rocks. That's the first rock formed from magma. All rocks were at one time igneous rocks. Now, we'll get into how they became other rocks later. Okay? Won't worry about that now. Here is a key statement here, and we're going to refer to it time and time again. The cooling rate of that magma determines the texture of the rock. Okay? Determines the size of the mineral crystals, which determines the texture of the rock. Now, here's what we're talking about. Notice here it says all igneous rocks are either formed above or on or near the Earth's surface or below the Earth's surface. Okay. If they were formed at or above the Earth's surface, the odds are the cooling rate was very, very rapid because they were hot igneous rock or magma below the surface. When we came to the surface, they cooled very, very quickly. Okay? So the cooling rate determines the texture. Usually those rocks are very fine texture because the minerals didn't have a chance to group together slowly. They had to do it quickly. So the bonds, the chemical bonds that make the minerals, they were few and far between. So it made for a very fine texture. Okay? Now those rocks that were cooled way deep in the Earth's interior and cooled very slowly, those minerals were allowed to form very large crystals. The very large crystals have a very coarse texture. Okay? So that's what it means. The cooling rate determines the texture. The cooling rate also usually is associated with the temperatures at which they happen. Okay. Is this the shot? Cold. Cold. Okay. Cold. Okay. Now, cooling rates determine the texture. The more rapid cooling rate, meaning rapid change of temperature, usually makes fine textures, very small crystals, whereas very slow cooling rate usually makes large crystals. All right. Now, along that same vein are a couple of other sub-classifications, but it's basically talking about this. Formed from magma above or on the Earth's surface or below the Earth's surface. If these rocks were formed below the Earth's surface, here's the way I remember this. In the Earth's surface, down in there, they are intrusive igneous rocks. Formed beneath the surface, in the Earth, slow cooling processes, so the cooling rate produces large crystals. And with large crystals, you get coarse grain. So there's your coarse texture. So this is tying two of the things from here, the previous side, the left-hand side, into this. Intrusive igneous rock formed beneath the Earth's surface, slow cooling rate, forming large crystals, that creates a coarse grain rock. Here is an example of this. Now, this doesn't look necessarily all that coarse grain, but it is. If you can see a blow-up of this, that's a fairly good-sized crystal right there. And there are other good-sized crystals scattered through here. It's just hard to see. It's a really rough picture. But this is a piece of granite. Granite is coarse grain, because if you feel the surface of granite, now I'm not talking about the granite on your countertop. That is granite, with Melanie's here. If you look at that countertop, you will see, if you got granite countertop, you'll see large crystal faces there. It doesn't feel coarse, because it's been polished like crazy, okay? And that's what makes a really slick, shiny surface. That's because someone's polished it. But if you look at that surface, you actually see crystals, individual crystals. That's coarse grain, okay? And this really shows that because that is very, very rough, okay? Now, extrusive igneous rock is from the exterior, the outside. These have made their way to the surface or above the surface. These form, now when magma is below the surface, that's what it's called, magma. When it reaches the surface, it's now called lava. So what was magma in the earth now is called lava when it reaches the surface. So it's formed from lava on the surface. It usually cools really rapidly because it's going from molten rock to ambient temperature. That's a fast cooling rate, okay? Now the other place that happens is not necessarily in the air. This also occurs underwater, okay? And underwater, it can be a very rapid cooling rate, okay? And when you have a rapid cooling rate, small crystals will form and you get a very fine surface. Now here's the most extreme of this. This is a piece of obsidian, which is chemical composition identical to the granite here. Do they look a lot alike? Nowhere close. Very coarse grain, large crystal size here. Basically no crystal size there. Obsidian formed very rapidly as the lava cools extraordinarily quickly. The molecules don't even have time to get into their crystal pattern, so therefore it's a form of what we call glass. Okay? Goodness, my nose is itching like crazy. The curved structure here is common. I can't read all this, but it's that type of material is a glass. There's not even any crystal structure there. Not only is it very fine grained, it has no grain. It is the crystal structure was not even allowed to form. I think I asked this question before. If any of you were Games of Thrones fans, I'm not. I've never even seen the TV show, but I've read several of the books, and in that author's imagination, the special swords that could be used to kill some of the real creepy crawly type stuff that was invading people was an obsidian stone, and that's the only thing that could kill some of those monsters, whatever they were. Not my favorite show or my favorite. I haven't ever seen the show, but the reading. He was a decent author. The first book or two was pretty interesting, and after that they kept going further downhill. But that was obsidian. It's very rapid cooling. So small crystals, the crystals don't even exist in obsidian. Okay. All right. Your text has a picture of granite that shows the crystals maybe a little bit more clearly, and they don't look like huge crystals, and they're not, but they're coarse grain, nowhere like the glass that's in obsidian. Okay. So, how do we classify igneous rocks? So like I said, there's classes and then there's subclasses and subclasses. Well, two factors that we use to classify igneous rock. One is the mineral composition. Okay, what are the dominant minerals in that rock? And the second is the texture. And we just mentioned texture. That comes from the cooling rate. A rapid cooling is a very fine texture, small crystal size, whereas a slow cooling, intrusive igneous rock inside the surface of the rock, earth, those will be coarser crystals, coarser texture because they're bigger crystals. So, mineral composition, you have non-ferrous composition, and they say of the figure. Let me go and get the figure up here. All right. This is a pretty decent representation of igneous rocks. Okay? The non-ferrous, meaning not much iron in them, are all on this side of the table. They're on the left of the figure. Okay, quartz has 0 iron in it, except maybe for a few impurities. Potassium feldspars, very, very few. Okay, your sodium-rich plagioclase, which are plagioclase feldspars, they might be getting a little bit of iron in them, but these are your irons, the biotite. Okay, notice most of your rocks on this end of the scale have very little iron minerals, very little biotite. Let's go back to the granite. Now, actually, these colors are not far off, okay? Except that's sort of a greenish, the dark is a green, and the reason they do that, if they made it black, you wouldn't be able to read the writing, okay? So let's go back to the picture of granite. You see the very fine little dark areas there? Biotite. That's the mineral that contains a little bit of iron. You see others that are fairly tannish to brownish. Those are your feldspars. And then you see the whitish, those are your quartzy type minerals. So you see this rock has several minerals represented in it, and they're represented basically in these proportions. From say 0 to 30% quartz, from 30 to probably close to 80 or 85%. So that would be close to 50% potassium feldspars, which are the tannish type of color. You have some sodium-rich plagioclase, which are another type of feldspar, a little bit darker than that, and then you had the biotite, which is a dark-colored, streaky mineral that you can see in that. And looking at that, not far off of this. Okay? Go back to it. About half of this is sort of that tannish color. Now the white is sort of messing with this too. About a quarter of it or more is the light colored silicas, okay, quartzy type stuff. And then some of the darker that you see, the brownish type stuff, would be your sodium-rich plagioclase. So you can almost see those percentages right there. The whitish are your quartz, the tannish are your potassium feldspars, orthoclase, sodium-rich plagioclase are your sort of the darker brown, and then the blackish are your biotites. Okay. So, non-ferrous composition on the left of the figure. Sure, there's a little bit of iron in it, but not a lot. Okay? They're low in density. Why? Because iron is heavy density. Silica is light density, so that would be low in iron. Low density. Light in color, because here you have your whites and your tans, light tans. So they're light density and light color, so you can think of those together. Granite is the most common example. However, you have other materials that would be also. And but they focus on these. All right. So that's the non-ferrous composition. The ferromagnetic composition would be those more to the right. Okay? Now, still silicates. Okay? All these are silicates. It's just these are iron silicates, these are pure silicates, these are potassium and sodium silicate with some calcium in here. Okay? But the iron, large iron content, and also calcium and magnesium down that way, and that's why they're called in some cases ferromagnetic. This has nothing to do with magnetism. This has to do with magnesium. So we see the same word, magnetic. Sometimes it refers to magnesium, sometimes it refers to the quantity, the capability of becoming magnetized. Okay. So these are greater density, because iron is heavier than silica. Okay. Darker color, because iron is darker than silica. Okay. And one of the classic examples of down here is basalt. And when we get to the lab, while y'all are working on the computers, I'll be showing off some minerals pieces that we've found. I'll give you a clue here, and here's basalt. Basalt is very fine grained, but very high iron content, so it's very dark colored. Gabbro is coarse grained, same thing. About the same density as basalt, but very coarse grained, large crystal size. I run into a lot of andesite and diorite, so I'll just leave those names up there. But your coarse grain, light colored, low density granite. Okay? Now, hang on to these granite and basalts. You'll see these paired up over and over again. And I'll point those out to you in a bit. The fine grained granite would be called rhyolite, and I have seen a little bit of that, but usually not too much. Okay, we usually focus on granite, which is a coarse grain, light colored, and basalt, which is very fine grained and dark colored. I was trying to think of anything else we needed to talk about now. I know a lot of stuff will come up later, but the example here, dark color, great density, is your salt, which aren't the heaviest and the darkest. When you get way, way, way deep, that's when you start getting olivine, which is almost pure iron. I mean, it's got silica in it. This is 45% silica right here. So it's still got quite a bit. Up here, it's 75% silica. Okay, so it's much, much greater. All these are silicates. It's just those are very high iron content. And here again is the ferromagnetic, ferromagnetic minerals, as opposed to the non-ferromagnetic minerals, which are your lighter colored granites and other things. Okay. That was it for igneous rock. Okay. Before we move away from this, now this isn't strictly having to do with igneous rock, it's just the page it happens to be on. The cost of mining mineral resources. It is a nice little blurb. It maybe open your eyes to expense of all this stuff, but obviously there's a hunger for the material. And I think it's worth a read. You may even find something to do your paper topic on there. Now, bottom of page 446 is a different picture of obsidian. Here was one right here, made it look quite a bit darker. This is more of a brownish kind of color, but it's this one actually has a quarter in the one in the book. Show you just how big a chunk of rock that is. Okay. Okay. All right. Goodness, my head is clogging up on me. I'm feeling really almost dizzy. There is an example here, 17.3, igneous rock classification based on proportion of the minerals present which is basically what we had in this figure here. It really is a good kind of three-dimensional graph here that relates these things together. And based on that figure, it gives you several things to answer, and it's really a pretty good example there. I'll leave it to you whether you really want to pursue that or not. And there's a lot there, so I'll let you look at that. 17.3, okay, this is getting into sedimentary rock. So, right-hand column, page 447. Igneous rock that came straight from magma, or lava if it was on the surface. Okay? What sedimentary rocks are, now this is a sort of a difficult transition here, because I'm going to talk about some stuff that we're going to cover in another 2 or 3 chapters later down the road. Okay? All rock, during its lifetime, gets battered around, bumped around, ground around, and over time, basically, is going to be in the process of falling apart, right? Think of a mountain. The mountain's exposed to water, temperature extremes, freezing, thawing, all sorts of stuff going on. And mountains, typically, if they're growing, they get more angular. If they're declining, they get more rounded. Think of the Appalachians. Very rounded mountains. They've been around an enormous long time. Those are highly weathered rock. Now the Rockies out in the west, those are a lot more angular and not nearly as weathered. But they're still undergoing weathering. Wind, grit, water, snow, ice, all that tends to break down the composition of those rocks. Now, when the rocks do break down, they go into small little pieces. Okay? That's one thing that can happen. Like, have you ever heard of sandblasting? That's when you take sand at high pressures and fire it against a wall of a building, outside the wall preferably, and you knock off all the lichens, the mold, the mildew and stuff that is growing up on the outside. You get a fresh, clean look. Okay? Well, that's what the wind does with particles on rock. They blow it into it and they chip off the external pieces. Now, the external pieces themselves, and we'll talk about this in later chapters, they have little cracks and crevices. Water gets in there, it freezes and expands, it cools and things. And then another thing that water does is either sedimentary rocks are either formed from particles, pieces of rock that have been chipped away from one means or another, or from dissolved materials. Water does a couple of things. Up at Smith Lake, my wife's family had a plot up there, Smith Lake, in a really rural area of Winston County. And ultimately, they first camped there, then they had a trailer there, and then later they actually built a little cabin. Well, when Karen's parents were ready to retire, they said, we, the couple who didn't have any kids, you buy the lake house. It wasn't a request, it was an order almost, you know, y'all can buy the lake house. Well, they wanted to set up their retirement home and they wanted to get something on one level and stuff. So we bought the lake house, and when you walk around or in the area, the places where water has run down, especially pretty rapidly because there's some steep inclines there, you see the rock has been sort of chiseled out by rapid movement of water, because water carries with it little sand and other particles, and they are constantly wearing on the rock, shaping it, okay? Those particles, after a while, settle out. Those are the formation of sedimentary rocks. The other thing that water does, it dissolves materials in the rock that are there, holding the rock together, and now it separates them. So you have particles that are separated, but also dissolved materials from previously existing rocks. Could be igneous rock, could be other sedimentary rock, could be metamorphic rock. Other previously existing rock, as water and other materials break off little particles, and also water dissolves materials, these form new rock, okay? These sediments are accumulation, and they're accumulations of a variety of things. Now, when you see these words, silt, sand, and later we'll talk about clays, and we talked about clays in the last chapter, the only thing that separates them, not the mineral or material composition of that, what separates them is particle size, okay? Let's start with the sand. I don't think I had some dimes and I gave change somewhere, and I don't think I have any dimes left, but let's see if I do. No, I don't. All pennies and nickels. Okay. Let's just take a penny. Penny's a little bit thicker than a dime, not much. Yeah, you got one. And if you had two of these pennies or dimes together, that's going to make, just imagine if you had some particles, say in your shoe that was the size of that. These are about 1 millimeter thick, maybe a little more. Anything 2 millimeters down, that's what makes the sand. It doesn't mean it has to be the white stuff at the beach. That, of course, is sand. It's about 2 millimeters or less in size. But it's also, that's what makes the sand the sand. Now, let's go to the finest, the clays. Now, I said this before. Take a dime and imagine slicing that dime, imagine this, into 1,000 equal slices. Those are really, 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 really small, right? Two of those together is the largest size of clay particles you'll ever see, 2 microns or less. Now, in between the microns, 2 microns, and the, say, half of a dime or something like that, that would be sand size. In between those are silt size. So the difference between these silts, sands, and clays is all a particle size difference. And here's how I think of those three. A sand is something, when you rub it in your fingers, it feels gritty. You can feel the individual particles there. If you rub a silt between your fingers, it feels like flour. No grittiness at all. Really slick, right? If you had clay particles, those are so small you can't even feel it. Okay, those are 2 microns. 2/1000ths of a dime in thickness is the largest clay particle you could have. Okay? So, these sediments are particles, particulate sediments. We call them clastic sediments. These are accumulations of silt, sand, or other materials that settle. The particles settled out of water. We call these clastic sediments, accumulated from rocks at various stages of breaking down. That's what makes a clastic sediment. Clastic sediment, okay? A particle that used to be part of a rock, okay? It could be sand, silt, or clay. And you'll see this table over and over and over again. This part we're dealing with the upper part, clastic sediments. Now, if these particles were actually larger than sand, larger than 2 dimes put together, we call that conglomerate or breccia. Think gravel. Things more of the gravel size. If those are what make up a rock, that's conglomerate or breccia. I don't know if that's breccia or breccia. I think it's breccia. Okay? Now, what's the difference between those two? We'll see this coming up a little bit later, so hang on to that question, but we'll get to it later. If it's sand size, that's 2 millimeters or less, then you form sandstone. And I'll show you, while y'all are doing the lab, I'll show you some samples of sandstone. Some that's really hard and some that's not so hard, but every one of them, you feel the surface, you feel the grit. You feel the grit. Another clastic sediment, smaller than sand, would be your silt or your clay. Clays are so incredibly tiny you can't even see them, so you can't tell the difference between them and silt. But you form either siltstone, if it came from silt, claystone, if it came from clays, or what they call shale. Now what's different between siltstone, claystone, and shale is how it was layered. Shale always comes in sheets, okay? The sediments landed in sheets. The sandstone or siltstone could have been in chunks, not sheets, okay? We'll talk about the others later, okay? Maybe even on the next slide. But let's just focus on these. Clastic, meaning comes from particles, sediments from particles. They can be large particles like gravel, conglomerate or breccia, small particles like sand, gritty type material, or silts or clays, which are slick, very slick materials. Now there is a company that makes wood stoves, and they make them out, and this is from Vermont or somewhere, they make them out of what they call soapstone, which would have to be some sort of siltstone or claystone. So slick that you don't even feel any grit. It feels like soap. Literally feels as fine as soap. Okay. So let's go to the second type of sedimentary materials. Oh, okay, sorry. This is talking about those particle sizes again. Anything bigger than 10 inches, pretty good size, right? Close to a foot. Those are boulders, okay? Now, 10 inches is a pretty small boulder, but it's a boulder. Anything between, say, 8/10, or let's say 1/10 of an inch to 10 inches, that would be gravel. Now, if this was formed into a rock, that's where your conglomerate or breccia comes from. Now, here's the separation between those two. Conglomerates are rounded fragments. Breccia are angular fragments. Now, that's one reason I say breccia, because that's a hard C angular fragments. If I said breccia or something like that, that's softer sounding, that wouldn't sound angular to me. So I say breccia, meaning angular. Conglomerate, well, that's a hard C here, but ilm is sort of a soft sound, so that's a rounded fragment. Conglomerate is a rounded fragment. Breccia, angular fragment. We'll see a picture a little bit later. Okay, now, that's gravel. Stone, rock made out of gravel, sedimentary gravel particles. Sandstone, that's anywhere from 2 millimeters, that's 2 dimes together, down to pretty small, 1/16 of a millimeter. That's pretty small. Your silt, and they use the term dust here. I like the term flour better, but dust says it too. Dust doesn't have any grittiness to it. Silt doesn't. Sand does. You can feel the grittiness of sand. Here you can't. This is incredibly small, okay? And these form siltstone, of course. Clay, and they say are dust again, and again, clay particles are so incredibly tiny, you can't see them without an electron microscope. A regular microscope, you won't even see the crystals. So basically what you see of clays are chunks of material that are made up of many, 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 many millions of clay particles. But that will also be a dusty material. But these are less than 2 thousandths of a dime thickness. Okay, so really, really fine. Now, they say siltstone and claystone are also called mudstone. It's shale if it splits on parallel planes, if it's layered in sediments. Sedimented in layers, I'll say that. Okay, So these are still all talked about, the sedimentary, the clastic sediments, the sediments from chunks, pieces of old rock material. Okay. The other are chemical sediments. Now these also originally came from rock, probably at some point back there igneous rock, but these are chemicals that have been dissolved. Now water is a great dissolver, but especially if you get a little acid in the water, and most rain is slightly acid, or if you have acid rain, which comes from industrial pollution, then you can really get some chemical solutions coming out. These are formed from dissolved rock materials. Okay? The dissolved rock material, either the water or the other chemicals in the water have dissolved the materials that were there, and now they re-solidify. Okay? Now, here are three paths of sedimentation here. I'm going to take you back to my first college chemistry class. We had a lab with it, and in the lab we had to do a series of experiments. And the very first one they had us do, they had clear water, okay, and they dropped a drop of chemical in it. And this chemical was silver nitrate. And I don't know if any of you are familiar with silver nitrate. In the old days, I don't know if they still use this or not, but when a baby was born, especially if there was a fear that there may have been some disease in the birth canal, especially, I'm trying to remember which one it is, some bacteria that causes blindness. I can't remember which one it is. When a baby is born, they drop silver nitrate into their eyes. Okay? I know my mom told this story many times. I wound up being allergic to silver nitrate. Of course, they didn't know. I'd just been born. They put that in my eyes, and my eyes swelled up so big. They were just tiny little slits there, and I scratched them like crazy. I hardly had any fingernails, but I was scratching because they itched like crazy. I was a newborn baby. They knew right then I had sensitive skin to some of the materials. I think it was the heavy metal silver. Okay, silver nitrate I was allergic to. But that's just a solution. Well, what they did into that solution of silver nitrate, and it was still clear as a bell, you couldn't see anything, they dropped a drop of sodium chloride, table salt, which is a good clear solution also. But as soon as that hit the thing, there you saw white come out of it. What the white was silver chloride. Silver chloride does not dissolve in water. Silver nitrate did, silver chloride does not. So that's what you call a chemical precipitate. Precipitation from a solution. So you have minerals there, you have elements there in solution, but then they mix with others that come across, something comes out of solution. That would be a chemical precipitate or a chemical sediment. So you would have got a bunch of silver chloride, which would not have been pretty valuable because silver is expensive, okay? Now, another way that you can crystallize sediment, things come out of solution, if the water evaporates away. I think I gave this example in the earlier class. You are going to cook your beans for supper, and you put your water on the boil, and you know the beans are sort of tasteless, so you put some salt in them to give them a little more flavor. But then the phone rings, you go and get talking on the phone, and you forget the boiling water on the stove, and what you wind up with at the bottom of the pan? Salt crystals. They went into solution. When you put the salt in the water, you didn't see the salt anymore. But when they boiled, the water evaporated away, the salt crystals was left. Same thing here. When you get minerals in water, and boy, do we have lots of minerals in water, okay? Then if the water evaporates away, it leaves the mineral behind. That is a chemical sediment. I don't know how it is where you live, but do you ever get white deposits around your shower head? And you usually call it calcium deposits. That calcium was dissolved in the water evaporated away, and it left the sediment. Okay? That was a chemical sediment. Okay? Crystallization from evaporating water. And then the third one here is called biologic sediments. Okay, biological sediments. I mentioned several times the phosphate deposits down in Central Florida. Where did they come from? Where did those phosphates come from? Well, that was one time a bottom of the Atlantic Ocean, Gulf of Mexico, something. It was beneath water at one time. And the things died there, and they settled out in the bottom. And over time, more would settle out on top, on top, on top, on top, on top, on top. And finally, over a long period of time, all that pressure, all that weight, it changed them back to minerals. They were parts of living material. They heat, temperature, moisture, pressure, all this added up and changed it back to that apatite rock, which is our source of phosphate fertilizers. Same thing about limestone. Okay? You had minerals there in solution, things biological in solution, and then they settled out in that biological sediments. To me, this could be either plastic or chemical, but generally probably a bit more on the chemical side. Okay? Here comes that same slide again. This time we're focusing on the chemical sediments. Okay, if the chemical in there was calcium carbonate, that formed the mineral limestone, the mineral calcite. Those calcite deposits redissolved into water, came back out, and formed limestone. Okay? Now, calcite, we'll see examples of calcite crystals. Big, beautiful, gorgeous crystals. Definitely crystals. But when they dissolve and then come back as a chemical sediment, limestone, you don't see those crystals anymore because they've been mixed up with other things. Some of those things may be biologic sediments, okay? They could be there. Another chemical composition, chemical sediment is dolomite, which is a lot like calcite. It's calcium and magnesium carbonate. That forms dolomite, and that forms the rock dolomite, okay? Dolomite's a mineral, dolomite's the rock too. The mineral if it's pure, the rock if it's mixed with other things. Okay, that's what a rock is. Chemical was gypsum, that's calcium sulfate, is gypsum. Yeah, calcium sulfate is gypsum. And when you combine that together with other things, you get gypsum rock. Boy, not much difference between the chemical name, the particle name, mineral name, and the rock name. And then one other is, the chemical is halite. Sodium chloride, when that comes out of solution, generally from evaporating water, but it could be other things, then you get your rock salt. Okay? Big cubic crystals of salt. Okay? Halite with the mineral, salt is the rock. That's a pretty ambiguous name for a rock, though, is salt. They call it rock salt sometimes. Okay, so either you have particulate sediments or chemical sediments. Both of these form sedimentary rocks. Okay, here are some of the pictures. Okay, this is a picture of limestone. Okay, mostly calcite minerals that have been dissolved and then reformed into a rock. Now they say, look right here, and you actually see a seashell that has been resolidified into that rock. So this is a biologic sediment that went into the chemical sediment of the limestone. Okay? Now this is a piece of sandstone. And you can see that there were layers and layers and layers and layers and layers of different chemically combined sands, but they've been pressure. I can tell there's pressure because these have been bent. And that's what created the pressure in them, the bending in them, different varying amounts of pressure. But this is sandstone. Now you can't tell while looking, but you can almost imagine that's going to be gritty feeling. It just has that appearance. That's sandstone. This, however, that's way bigger than a sand particle. That's a gravel particle. This is your breccia. Why breccia and not conglomerate? Because of the angles. You see these gravel pieces in here have distinct angles to them. So that makes it breccia. If they were rounded like pea gravel, and that was what formed the rock, then that would be conglomerate. Okay? The breccia are angled, the conglomerate would be rounded. There could be some rounded forms in here too, so there could be little bits of conglomerate mixed in with the breccia. That looks like that's a rounded piece there. Okay? This sample with something sized, something in other fragments. Oh, it's from Colorado, is what it says. Okay. And here's that slide again, okay? Told you to see it over and over. This is chemical sediment, calcite, limestone. Okay? The mineral in there is calcite. It was dissolved, reformed into limestone. But there's lots of other stuff mixed up in there. There's some sand in there, some quartz, some other things, but it's mostly calcium carbonate. Chemical sediment. Dolomite would be a lot like that, only a little bit grayer. This is a little bit whiter. Okay? Gypsum would be a lot like this, only probably even a little bit whiter than this. Halite could be very light colored as well. Okay? These are clastic sediments. This is sandstone here, and this is breccia here. So chemical sediment, sandstone, and clastic sediment, breccia, which is gravel pounded into a rock. Formed into a rock. Now you might ask yourself, what's the black stuff in between the pieces of gravel? That's the cementing agent. We'll get to that a little bit later, but that's the thing that water and other chemicals like acid and stuff will dissolve this stuff away, release those particles, and it goes back to being later formed more breccia or other materials. All of it goes through a process. Okay? We'll talk about that later in the chapter as well. Now, how are these sedimentary rocks formed? Now, this is especially pertaining to clastic sediments, sediments made up of particles. Okay? When you see the prefix, and sometimes it's a suffix, lith, think rock. So this is the rock forming process. That's what it says right here, rock forming process. Litho means rock. Okay? Two main parts of it. First, you have compaction. Okay, now a lot of times the sedimentation occurs from water. Water is washing the sand, the silt, the clay, the gravel down into somewhere, settling it out so it's being deposited. A lot of times that comes from water. It may be wind blown, but a lot of times it comes from water. Well, as layer goes on top of layer, on top of layer, on top of layer, the more and more weight squeezes and squeezes and squeezes out the water. That's your compaction. Before that, water was separating the particles. The more you pile on top of it, the more it squeezes out the water. But that water, as it goes, leaves behind some things that were dissolved in the water. Those things that were dissolved in the water are then the parts that do the cementation. So first you have compaction, then you have cementation. Here, the spaces between those particles are filled with a chemical deposit, generally that came from the water, that was dissolved in the water, that came out of solution. The chemical deposit binds them together, and that's what makes it a rock. So looking back, I'll come back to this slide in just a second, but looking back to that breccia there. And also, you can't see it in the sandstone, but the same thing's true here. The stuff in between is the cementation, and that's holding the chunks of gravel together. This is sand particles, but something's in between those sand particles holding them together. That's the cementation. First you had compaction, where you press these closer and closer together, squeezing out the water. When the water left some of the material dissolved in the water, that became your cementing agent. Okay, so I'll go back if you just still need to write from that. So let's see what slide follows that. This is a decent, a little bizarre. Okay, your sediments are deposited, and at first, when they're first deposited, they sort of pile up on each other, and you have a lot of pore space in between. Okay, and most of that pore space probably has water in it. Okay, and that's what keeps them apart. But when you pile more and more and more, and what they call it is overburden, on top of it, on top of that, on top of that, it squeezes out more and more, forcing those particles to kind of shift, squeezing out the water. But as it goes, it leaves behind some of the dissolved material that were in the water, and that forms the cementing agent in between the particles. And so the combination of compaction and cementation, that's what forms your clastic sediments. That's what forms your sandstone, your breccia, your conglomerate, your mudstone, your siltstone. All those other materials like that are formed by a combination of compaction and cementation. Now, the other thing involved is time. This has to go on over quite a bit of time period. And that cementing agent has to really solidify. Okay, it can't be somewhat loose, okay, or else it's not going to hold it together. So usually there's time and sometimes temperature involved with it too. Okay. Your book has a different picture of breccia in it. Let me fly back to this one. That was breccia, the lower right corner there. You see a couple of more pieces of breccia. One, the cementing agent is this one is a dark colored cementing agent. The one on the left in your book, figure 1715, is a reddish, pinkish looking cementing agent, and the one on the right in your book seems to vary between a grayish and a pinkish. Okay. Those are all examples of clastic sediments, actual pieces of material. Figure 1716 shows a sedimentary rock, different layers, different things must have been deposited over different time periods, but then all of them pressed down from above, squeezing out the water, leaving the cementing agents and holding it together that way. Now, the next picture is that one in 1717, limestone, a sedimentary rock formed underwater, and sometimes remains of marine organisms are actually found in that limestone. And that one picture we saw right there has a shell in it. You can see that. Now, so that's your lithification process. 2 steps: compaction, cementation, to get your hard sedimentary rock. All right. Moving on to Okay, before we move. Page 449, a closer look. Asbestos. Good, bad, or indifferent? Asbestos. Anybody? Good, bad, or indifferent? Most people, if they hear asbestos, they think, bad, bad. Okay, stay away from it. Don't have it there. My sister frets about the flooring in her house. She's afraid it may contain asbestos. I say, Jane, unless you're going to be grinding that stuff up, it can't hurt you. It's all embedded in the floor, okay? It's not going to flake out, okay? It doesn't do that, okay? But people are scared to death of the word asbestos. I can't remember exactly the details of this, but it was something with my wife's family. Someone was really big on some of the old videos that they had of really old television shows. Do anyone remember George and Gracie? George Burns and Gracie Allen? When I was a real small kid, they had a comedy half-hour sitcom type thing, and they were two of the funniest people I could remember seeing. Well, someone was running some of those. Those were really, really old, and they ran the commercials too, and the commercials were bragging about asbestos, the greatest, building material ever. And what was great about it was it would not burn. Okay, you could have a propane torch, a welding torch, and hold it onto asbestos. It will not burn. So this is a flame retardant, a fire retardant. This is a great thing to have in your building to keep them from catching fire and burning. Okay, they are also good insulators. They can keep hot water hot and cold water cold. There's just lots of uses for this asbestos, until they found out it called asbestosis, I guess it's called. It really damaged lung material and caused lung cancer. And so people started leaving asbestos. Buildings found with asbestos were shut down. They were put under body bags almost, and people went in all suited up and got all this asbestos out of there, or else the building was destroyed. But even that, the destruction process, you worried about asbestos getting into the air. So asbestos is a bad, bad word now. The trouble is, there are two types of asbestos, brown and blue asbestos. It's an amphibole material commercially called brown and blue asbestos. The other variety is made of a chrysotile. It's of serpentine value. It's called white asbestos. White asbestos is asbestos mined and most commonly used in North America. It's only the amphibole asbestos, brown and blue asbestos, has been linked to cancer. But guess what? No one will touch the others because its name is asbestos. So no one wants to mess with it. So anyway, that's a nice little blurb. If someone wants to read it, you might find a useful paper topic there. Science and Society tops the next page. Using mineral resources, there's a good little blurb there. Some questions you can think through. If you find that really useful, you can maybe write a paper, use one of those as a paper topic. Now we're ready for metamorphic rock. Again, what's metamorphosis? And by the way, morph means to change. Metamorphic is a big change, okay? And what this means is like caterpillar to butterfly, enormous change. The end result doesn't look anything like, in any way, shape, or form, much like the original, okay? There's a few other examples, but I guess I'll leave those alone. Here's what metamorphic rock. Previously existing rocks could have been igneous rock, could have been sedimentary rock. It could have been other metamorphic rock. But now it's been changed. Remember in the last right at the end of the minerals, we talked about altered minerals. What alters those minerals? Heat and pressure. Well, guess what changes these rocks? Heat, pressure, but also hot solutions, and they change it into distinctly different rock, just like before, changed it into distinctly different minerals. And these will occur simultaneously and in conjunction with each other. Often these are associated with geologic events, movements of the crust, lots of pressure, lots of temperature, lots of things going on there. That could cause metamorphosis of the one type of rock into another. Heating and hot solutions from magma intrusion, that could change the rock that's there. Not melting it, it's just putting it under more pressure, more heat, changing the crystal structure. The temperatures must be high enough to cause recrystallization, but not melting. There's a fine line there. You got to have it hot enough to change the crystal structure, but not hot enough to remelt it. Because if it melts, if it comes back again, it's now igneous rock, not metamorphic rock. If it doesn't melt, but changes crystal structure, that's when it becomes metamorphic rock. So here are some examples of this. Now, I don't know if you remember, we talked about chemical sediments. We talked about limestone and dolomite. These are chemical plastic sediments, where you had mudstone or claystone, siltstone, or I said it could be shale if it was in layers. Well, here's we're starting with shale. Layers of plastic sediments, very, 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 very small particle size, silts or clays, in layers. Compaction, cementation has occurred. You have this shale in layers, but then it moves down, 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 deeper and deeper, more pressure, higher temperatures. That shale can actually change to slate. Well, what is slate used for? Have you ever heard of slate? We happen to have a piece in our downstairs bathroom my wife picked up in New Orleans. This is what they use for shingles. Pieces of rock that are in such sheets, they cut them into sizes and use them for shingles. Our church in Southside Birmingham, the old part of the church has slate shingles. It's a green colored shingle, really pretty, really durable, but when it leaks, it's really expensive to repair. Okay, awfully expensive. Well, that's slate. That's shale, sedimentary rock, plastic sediment that have been undergoing more and more pressure, change the crystal structure into slate. Much harder, much more durable. Okay? Well, if that slate undergoes more pressure, more temperature, it can change to a schist, which is a second kind of metamorphic rock. It comes from another metamorphic rock. And if that undergoes more pressure and temperature, it can actually deform and become a nice rock. No. Okay? Now, remember a picture early in this chapter of a big chunk of rock that had all these weird shapes and bends and layers in it? That was gneiss. It had one time been shale, later formed slate, later formed schist, finally formed gneiss. Okay. What's this at the bottom? Is granite a metamorphic rock? No. What happens if you keep adding heat to it? And more heat? It melts. And if it recrystallizes after that, no longer metamorphic, it becomes igneous again. So not only does all rock once igneous rock, at some point most rock is going to become igneous rock again. Okay. So let's go to a different kind, a chemical sediment, limestone, made up of calcite or dolomite, minerals that have dissolved, reformed, and made limestone. Limestone, under a lot of pressure and temperatures, actually will recrystallize to form marble. Now, I'll show you some samples of marble. It's one of my favorite rocks, okay? And when my wife said she wanted to do the countertops in marble rather than granite, I went, yes, okay. Well, I really like marble, okay? But if it undergoes more heat and temperature, more heat and temperature, more heat and temperature, it actually melts and goes back to, comes out of solution as calcite, which is an igneous rock again. So this is actually the mineral calcite. Sandstone, another type of sedimentary rock, but this is classic sedimentary rock, but these are sand particles. This was silt and clay, so this is that rough stuff. You undergo heat and temperature with that. It changes the crystal structure and makes what they call quartzite. Now, some of the countertops I've seen they call quartzite. I don't know if that's naturally occurring or if man has done that. If it's man-made, it wouldn't be a crystal, but it could be that. But if that undergoes more heat and temperature, more heat and temperature, more heat, ultimately it's going to melt. And when it comes back as quartz, that's sediment, that's igneous rock again. So you see it goes through this whole cycle. And here's even igneous rock, a fine-grained igneous rock, that more heat and temperature acts on it, and it becomes a schist. And sometimes you can't tell, was this a sedimentary base for it, or was that fine-grained igneous rock that became schist? You can't tell for sure. And then after a while, more heat and temperature on it could metamorphosize it again to be nice rock, until more heat and temperature melts it again. It goes back to being igneous rock. So this is somewhat of the cycle. Now, that figure is on your page 451. The top of 451 is the person behind the science. They have these in just about every chapter, I believe, every one. Victor Moritz Goldschmidt, okay? He was Norwegian. Victor Moritz really sounds, that Goldschmidt could be German, but it's, he was a Swiss-born, so there's the German part, Norwegian chemist. So evidently the Moritz was the Norwegian part. But he was one of the leaders in, I think, geochemistry. He helped basically found the field. And that's what we've been talking about, is a lot of that. Now, remember we classified igneous rock into intrusive igneous and extrusive igneous. We, different ways, and then the metamorphic rock was sedimentary, clastic or chemical sediments. We classified that. How about metamorphic rock? Does it have any classification? Well, yeah, it does. And here's the classification of metamorphic rock. We basically classify it by its foliation or not, okay? So, have any of you ever heard of a portfolio? Yay or no? Portfolio? It's usually a collection of samples of your work or something like that, your portfolio. If you're a designer, you would have your different designs in there, okay? Well, that means pages, sheets of things. Folio means sheets. So foliation would be the alignment flat crystal flakes into sheets. And that's usually how your metamorphic rock happens. The pressure and temperature has sort of flattened out the crystal structure until you get sheets. Or not, okay? And if you have sheets, you define it by the foliation. It's caused by the pressure on the parent rocks that sort of smushes them into sheets. That's a really gross way of saying it. The rock cleaves along planes between the aligned grains. That means it breaks that way. It comes apart that way. So you have varying ways of foliating, or you have rocks that are non-foliated. The parent rocks consist mainly of one mineral. The grains are not aligned into sheets, so the crystals have remained three-dimensional. Okay, and sometimes quite hard. Okay? So here's your classification scheme. Okay? If it's non-foliated, that would be things like your quartzite and your marble from the last one. Remember, the quartzite was that was originally sandstone. Quartzite, you know, that was three-dimensional. Quartz is still a three-dimensional crystal, really hard, rugged, and stuff like this. Marble, limestone was, you know, some of the pictures in the book look like it was layered, and probably was, but the crystal structures are still non-foliated. So your marble is a non-foliated crystalline structure. Okay? Very finely foliated, that would be your slate. Okay? That was the first one here. The shale that metamorphosized into slate, that was very finely foliated. Okay? Going back and forth. Very finely foliated. The finely foliated would be the schist. Okay? That was the next step. Finely foliated, very finely foliated, finely foliated, and then the coarsely foliated is your nice rock. And that came either over here or here. So the schist, finely foliated, either way here, and nice was your coarsely foliated. Just the way they classify these metamorphic rock. Either non-foliated at all, still three-dimensional, very finely foliated, easy to separate, that would be your slate. Finely foliated, a little bit harder to separate, would be your schist, and your coarsely foliated, which would be pretty hard to separate, but you still see the sheeting there. That's your gneiss. Okay. And this is that same figure we just had. Here is that different picture of marble. Okay. And this is not polished marble, so you don't see it. There's no. The calcite crystals are recrystallized from limestone during metamorphosis. Okay. There's that same picture of your gneiss rock. Okay. And you see that's really coarsely foliated. It would be really hard to split that into sheets because there's so much pressure and temperature on it. It's gotten all gnarled, and you see it. One time it was sedimentary rock, it was layered rock, but then it metamorphosized to shale, and then to slate, and the schist, and finally to this nice, very coarsely foliated, and they say that's one of the oldest rocks they found. It's undergone a lot of temperature and pressure changes over many millennia. Okay. Any questions? Now, last topic, and actually everything up to now has been leading to this, and this is the rock cycle. And we're going to see this over and over. Just about every chapter is going to have some type of a situation that relates to this. Rocks are transformed into new types by the Earth's interior and exterior dynamical processes. That means they're always changing. Now the changes may be slow, grindingly slow, but they're still always changing. Continents, believe it or not, are moving. Not perceptibly, hard to measure, but they are. Seas advance and seas retreat. I'm not just talking about the tides, but long periods of time. Okay? Weathering and erosion by wind and rain are always happening. We'll see this again 2 or 3 chapters down the road here. But all these things are always happening, and as they happen, rocks are being transformed. More pressure, more temperature, they're metamorphosizing, they're breaking down, they're getting put back together, they're being compressed, compacted and cemented. What was rock is now rock. Okay, all this is constantly going on. And this figure is one of the best I've seen to indicate that. What was all rock at one time? What kind? What class? All rock was at one time igneous rock. So let's start with igneous rock. Okay? Igneous rock can be weathered, eroded, worn down by wind, by rain, by moving water, by various things, broken down into pieces. So it's no longer rock, it's little pieces of gravel, boulders, sand, silt, clay, whatever. And then those pieces sediment out and form sedimentary rock. The lithification process is the process of which the water gets squeezed out by compaction and the cementation binds it together to make sedimentary rock. And here they've made it so it looks like layers of sediment there. Okay? Well, guess what? This can be eroded and weathered again into pieces again, and then it sediments out again and goes back into another form of sedimentary rock. So here's a little short cycle here that's a rock cycle. It goes round and round. Or this sedimentary rock can get more and more overburden on top of it, more and more heat, more and more pressure, and metamorphosizes to metamorphic rock. And now you see some prettier grains and things like this. This is usually very hard, very resistant to change, but it can be eroded or worn away, and if so, it goes back into sedimentation and goes back into sedimentary rock again. Or more heat and more pressure might change it, melt it again, goes back to magma, and magma, when it cools, becomes igneous rock again. Or this igneous rock, rather than being broken apart, gets pounded on and built on, and more pressure and temperature, it metamorphosizes into metamorphic rock, and then it either goes back to sedimentary rock or it goes over to magma. But the cycle can go round and round, all different ways, all different paths, many times around. That's the rock cycle. It never stops. They're always changing. It may be igneous rock for many centuries or millennia, but it's still going to be worn away or pressured or something into changing. And the whole process is always happening. Slowly for sure, but happening. Always happening. That's the rock cycle. Any questions? That's the last slide. How are we doing on time? 3:15. We've got 30 minutes left. Like I said before, next meeting on Thursday, we will have the last 30 minutes will be the test on chapter 17. Whatever else we get done, the last 30 minutes will be the test on 17. Okay? The 2 hours before that will be the lab that's associated with 17. Now, it's not anything special on 17, it's just another lab that ties all these kinds of things together. A little bit maybe of the astronomy part, but yeah, it's just a lab. To get ready for the test, say it every time, I'll keep saying it, nothing replaces reading the chapter. Please read the chapter. Better before I talk about it, but even then, read the chapter. Okay? Then there's a summary here, and this one, about maybe normal length, maybe a little on the short side, but several words in italics that are important to pay attention to, and you'll see that most of those show up in the key terms here, which again is a little bit shorter list than most of them have. But then we have applying the concepts. And again, maybe a few fewer questions than normal, only 43 here, but these are multiple choice questions. If you know how to answer those and answer them correctly, and the correct answers are listed here, then you've got a really good grasp on this material. Now, you won't see those specific questions, I don't think, on the test, but you may see, you definitely will see ones that are related to the same thing these questions are asking about. So that's a good study guide. Okay? Then there's questions for thought, 19 questions here. That's a bit on the large side, maybe a little bit more than normal. There's 4 for further analysis. That's about normal, a little on the short side. And then there's the invitation to inquiry, building rocks. You can look at that if you want to. Maybe you'll get something. And then there's the parallel exercises, which are a lot like the little examples they scattered through the text. You certainly can work on those if you'd like. There won't be much that you will see from that in your on the test, I don't think. However, there's a few things, like here's Galena is mentioned here on question 7 on the Group A group, and I believe Galena is going to be one on the lab that we'll be doing in half an hour. So you might see some things in here that you'll find interesting. All right, any questions on chapter 17 before we move to 18? Now, this is not a bad break time, but we are going to be changing rooms in 30 minutes to go to the lab. So I think that would be a little more logical break time. But if you really need a break now, this is not a bad time to take one either. What you think? Wait till lab or break now? Break now or forever hold your peace? Okay, never mind. Second?
I just gotta go to the bathroom.
Okay, let's try to keep it less than 5 minutes. For sure less than 5. And just do a real quick break here. And turn on conductor first. I forgot. Okay. All right. Any questions then on chapter 17? All right. Well, chapter 18 uses a lot of the same information and background that we used in 17, and we talked about the earth shifting, continents moving. That's exactly what this chapter is talking about. We talked about the pressures and things like this. This is giving us the reason for some of the pressures. We talked about molten rock. We're going to hit molten rock in plate tectonics. We'll find out why some of it is melted. Okay? So that's chapter 18, plate tectonics. Here's the core concept on your page 458 also. Earth has an internal structure, okay, and it cycles materials, oh my goodness, there's that cycle again, between the surface and the interior. And then it has a picture here we'll see again late in the chapter, and these are some of the major plates of the Earth's crust, you might say. Actually, it's a little bit more than the crust, but these are the plates. Big one out in the Pacific, another pretty good size one, North America, a pretty huge one called the Eurasian plate. Much of Europe, just about all of Europe, and much of Asia, not all of Asia. There's the African plate, it's pretty good size. The Indian-Australian plate is a really bizarre one. And then there's a bunch of smaller ones, the Caribbean plate, here south of us. South American plate, I didn't mention that, it's a pretty good size one. There's a Caribbean plate, a Nazca plate, the Philippine plate, the Arabian plate over here. They list one here, they color one in and don't ever give it a name. The Antarctic plate is down here. Now that looks huge, but it really isn't that big because of the projection here. But then you have some little bitty ones like the Juan de Fuca plate, okay? One of the smallest ones, and yet one that really creates some havoc in places. We'll talk about these a little bit later. Let's first look, and this goes back to planetary formation, chapter 16, history of Earth's interior. We feel like the Earth was formed about 4.6 billion years ago when we were part of the solar nebula. Okay, now, Sun was about 5 billion years ago, approximately. So it had been formed and there was still some residue floating around, flying around out there, and that's when the planets were sort of formed up. It was still pretty hot and blistering and sort of gaseous phases, and things began cooling and settling out, and that's about when they think the Earth was formed. The early Earth had a molten surface, and part of that was it had just cooled from a gaseous to a molten, but it was still being hit with just tons of other materials. They were just constantly impacting it, and those were very high energy, high temperature bombardments. So the Earth's surface stayed melted for a while. After a while, the surface did finally cool, and then is when it crystallized. Because it was molten, all those rocks were igneous rocks because they had crystallized from molten material. That's why all rock were at one time igneous rock. There weren't any sedimentary rock. There weren't any metamorphic rock then because it just cooled to be igneous rock. Okay? So all rock was at one time igneous rock, sometime in its past. See, this is the tie between last chapter. The heat accumulated from radioactive decay led to a second melting, this time of the interior. Okay? So the exterior had finally cooled, but, you know, the sun's explosions and stuff was all radioactive. And it left a lot of radioactive materials, and these, as they decayed, especially when the surface hardened, now all that heat was sort of trapped in there, and this melted the interior. Okay? That melting occurred, though, in pockets, not throughout the interior. Okay? We still have some activity of that nature. Okay? This led to differentiation. What that means is heavier materials settled lower, lighter materials went upward. You know, the melting and gravitational settling of heavy metals down, lighter materials up. This gave the Earth its present stratified structure. Okay? Remember when we talked last chapter about the Earth? The upper part are the lighter weight, the silicas, oxygens, and those kinds of things. The Earth's crust is 75% silicon and oxygen, almost 50% oxygen and more than 25% silicon, okay? And then the other heavier stuff, there's some of it out there. When you get down into the whole Earth, iron's the leading one, but that causes iron mostly settled out near the center. Some iron is on the surface, yeah, Red Mountain, you know, that kind of stuff. But this gave Earth its present stratified structure. We'll talk a little bit more about that. Now, what we have now is a crust of the Earth. Okay, we talked about that last time. And we'll talk about this more. Then we have another really thick layer that's solid. We'll talk about that. But then you have the core, and the outer core of the Earth is still molten. It's still liquid, and it's mostly iron. Why is that liquid? Because all the pressure that's on it from above, the overburden, pushing those molecules closer and closer together, yet their friction against each other, they're hot enough to melt, and that's why they melt. So the outer core is still molten, mostly iron. Sure, some iron silicates in there, but mostly iron. Now, at the Earth's center, though, you go back to being a solid. And part of the reason, look at the pressure there. 3.5 million atmospheres of weight, of pressure on that center. It forced it back into being a solid. Temperature there, about 6,000 Celsius, 6,000 degrees Celsius, which add to that 273, and that would be the Kelvin. Okay, that's pretty hot. Okay, pretty hot. Not hot enough for nuclear fusion by any means, but is still pretty hot. Oh, did anyone need that a little longer? So, this is sort of the history of how the Earth came to be what we see it is today. And it seems like, of course, we're living in a very short period of time here, but it seems like things have kind of settled out into kind of an equilibrium, okay? Who knows, maybe the outer core will slowly cool some more and more will solidify. Don't know, okay? Hard to say. But it has definitely not going through the big changes it did early on in its history. Let me turn in the book while y'all are looking at that to make sure I'm hitting everything. Okay, this is 18.1 we're doing now, and I think this is pretty much through with it. Everybody got it? Okay. So let's talk about evidence of Earth's internal structure. I think this is moving into 18.2. Okay? Okay, we've been talking about the structure seems to be here. What is evidence? Why do we think that you got an outer shell that's solid, but you still got the outer core that's liquid, but then it looks like there may be an inner core that's solid again? What is the evidence that that is the case? Well, part is, why do we have a magnetic field? Does anyone know what it takes to make a magnetic field? See, this is all stuff you would have had in the first half of the book had you had the first half of the book. What does it take to make a magnetic field? Anyone know?
Gravity.
Second?
Gravity.
One more time.
Gravity.
Gravity, is that what you said? That has a part of it, but that's not it. What makes a magnetic field anywhere, any magnetic field, is a moving charge. You have to have a moving charge particle in order to create a magnetic field. You have to. Okay? Now, well, where are the moving charges? Well, you know the Earth is spinning, right? And if it's just one solid rock spinning, there would be no reason to think there's moving charges in it. But we know we have a magnetic field, so therefore we assume there's got to be moving charges somewhere inside. Well, if the outer part is solid, but the next inner part is liquid, then when the solid turns around the liquid doesn't have to spin as fast as the solid. It can sort of sit there. And when that happens, especially since there's roughness in that boundary between the two, you're knocking off charges. So you have currents of charge. That would create a magnetic field. And that's one piece of evidence. The fact that we do have a magnetic field shows that we must have some inner part of the Earth must be liquid so that the outer part, which is solid, spinning around it, is creating that magnetic field. And we're mostly iron in there, and iron is definitely magnetic material. Another piece of evidence of the internal structure, the gravity effects. We know about what the density of the crust is. We wouldn't have as much gravity as we have if the whole Earth was the same density as the crust. So we know it has to get denser and denser the deeper you go. Otherwise, you can't account for the gravity we have. So the gravity effect, again, is evidence that the Earth's internal structure must be something like what we think it is. Okay? Heat flow. Okay? Whoa. We know there's heat in the Earth. Every time there's a volcanic explosion, a lot of that heat comes out. That heat has to be in there, and that flow of heat that we can measure, scientists have ways to measure that supports the concept of our internal structure. Okay. And then comes the biggies. Vibrations in the Earth. Why would there be vibrations in the Earth? Well, plate tectonics, but that we're not quite there yet. We know we have these seismic waves. And what produces these seismic waves? Earthquakes. What are earthquakes? They're places where one plate, this is getting into plate tectonics now, gets caught up on another plate, but they're trying to move past each other, and then suddenly there's a breaking of something. When that sudden break occurs, that's what is an earthquake. These seismic waves move out of that, okay? And so that indicates the structure is there. Okay, we can also get seismic waves from nuclear explosions. All shots, no country can hide a nuclear test because we have seismographs all over the world, so we can tell when there are earthquakes wherever they are, and we can pinpoint where they are and know how to respond to them. Well, those same seismographs detect nuclear explosions as well, so there's no hiding. Now, but wait a minute. How is this really evidence? Well, the way these seismic waves radiate tells us a lot about the internal structure. We'll see that, if not in this chapter, the next chapter. No, I think it will be in this chapter. So let's see. Yeah, this is it. Seismic waves. There are three basic classifications of these seismic waves. And just getting in here under the bell for the first big 10 minutes to spare is Bertram. We have finished chapter 17 today, which means Thursday we'll continue in 18, which we started, and then we'll break and have a lab that sort of goes with 17, and then we'll have the test Thursday in the last 30 minutes on chapter 17. Okay. So the first 2 hours will be 18, next 2 hours will be the lab that's sort of associated with 17, and then the last 30 minutes will be the test on 17. By the way, every test in here, if you haven't heard this before, you're hearing it now, will be, you can have a formula and equation sheet. So that's a good way to study. Okay. Now, let's get back to the seismic waves. Three different classifications of waves that come out of every earthquake. The first is a P wave. Now that P wave, there's two ways that I can remember the P, and they're pretty important ones. Okay? We'll first say it's a pressure wave. P wave, pressure wave, meaning it's compression. Okay? Now, a compressional wave is a lot like when I'm up here talking or you're talking. If you held your hand in front of your mouth, you feel a little burst of air. That's what makes the sound. Those are pressure waves, and that's what your ears are picking up. Little bitty pressure waves that are coming from my voice, from my larynx, sending out these pressure waves. Your eardrum is responding to those little bitty changes in pressure, and your nervous system translates that into sound. That's why you can hear. Some of you. Okay. So that's a pressure wave. These are also called longitudinal waves. Longitudinal wave means the motion of the particles. When I'm talking the pressure, they're going back and forth. Sometimes it's a pressure, sometimes it's a rarefaction. So it's back and forth in the direction of the wave. That is a longitudinal wave. Now, these are the fastest of the waves. So therefore, they get there first. So we also call these the primary waves. The first wave, first. Primary wave because they're the fastest wave. Pressure wave, compressional wave, longitudinal wave, they're the fastest waves, primary waves. Now, here's the key. Pressure waves, P waves, longitudinal waves will go through solids, they'll go through liquids, and they'll go through gases. That's why going through gas, that's why you can hear me now, those who can hear me now. Okay? But if you've ever been in a swimming pool and gotten down under the water, you can hear sounds there probably a lot more distinctly than you can, maybe not distinctly, but they're clearer or louder under the water. And y'all remember the old westerns when the bad guys or the Indians or whoever it was wanted to know if the train was coming? What did they do? They put their ear down on the track. and you could hear the train way further through the metal than you could through the air, because the pressure waves go through solids, they go through liquids, and they go through gases. Now, we're not interested in gases and seismic waves, but they do. Those are the P waves, the primary waves. The S waves, two ways to remember those two. These are shear waves. Now, what do we mean by shear waves? Where a pressure wave is a longitudinal wave, the direction of the disturbance is in the same direction that the wave is promulgated. The shear wave, they go in opposite directions. And I think of a shear wave, I think back to my boyhood, okay? And this is really bizarre, but it's one thing I really like to do. If we ever had the hose strung across the yard that we're watering something, I like to go get that hose and do this to it. And then I watch the hose make a little motion and it goes down the way. The stronger I can do it, the further it would go. Of course, dampen out. That is a shear wave because the motion is up and down, but the wave goes that way, perpendicular to the motion. The compression wave is in the same direction of the motion. The shear wave is perpendicular to it. The action is up and down, but the wave goes perpendicular to that. That's called a transverse wave. Trans meaning against, opposite. This is doing this, that's going that way, okay? Pressure wave, longitudinal wave, it's in the same direction. These are transverse or shear waves. S, shear, transverse. They're second fastest. So they're secondary waves. S wave, secondary wave. They don't move quite as fast as the P waves, the primary waves, the compression waves. And they don't go through liquid. Okay? They don't even go through air, but who cares about that? There's no air. But they don't go through liquids. Because if you think about, can you imagine a tub of water and you do this in it? You don't get any waves going in that direction. You get waves that do this, because a liquid doesn't transmit the same way a solid does. That hose is solid, so it will transmit your wave. Okay. And then the third kind is your up and down crest and trough wave. This is just like a water wave, okay? It's a surface wave. And, goodness, my nose is itching like crazy. Must be going to have company, right? This is a surface wave. Much like water waves, these are the slowest of the waves. But of course, you don't see them or sense them until they get to the surface. Now, I don't know if you've seen pictures of when they did do something like have an atomic explosion or just any massive explosion. And you'll see the big boom happens and those pressure waves and people, they usually have ear protection because you can damage your ear by the pressure that comes off of those. But then after the big boom, you see little waves going along the surface of the sand or whatever it is, and if it's over water, and they go out like this. Those are the surface waves, up and down. They're the slowest. So they occur where the P or S wave reach the surface, and then they form the surface waves. Now, we're not as concerned with those. These are the primary ones we're concerned with, primary and secondary, P and S waves. Okay. All right. Now, here's another example. I gave talking as a primary wave. Primary wave, a compressional wave. You could also, if you could imagine a spring. Now, the thing that's so artificial about this, I can't imagine holding a spring up like this and it staying level. It seems like it's going to sag. So they're trying to make the illustration. This was a really stiff spring, and then you took it and did that to it. You'll see this wave move down the spring. You'll see the compression move down, but then the rarefaction where you pull back away from it. Now, they left off the pressure. The contracted part should be here, the rarefacted part there. Compacted part there. See, they left that off here, and the rarefacted here, and it moves down. The motion is in the same direction as the promulgation of the wave. Whereas, this is my hose on the ground, a tense string here, you go up and down with it, and the wave goes up and down and travels down the string. Okay. that is a shear wave, a transverse wave. This is a pressure wave, or a longitudinal wave. So those are the differences there. They don't show an example, I don't think, of a surface wave. All right. All right, I think we're just about at the time to stop, right? Who has a clock? Huh? 3:43. Let's see if there's a better stopping place. This is probably as good as any. Okay. Yeah. So let me just mark here. That's where we'll begin next time. Okay. Did y'all need the previous slide any longer? Or were you copying on this one? Okay, yeah, okay. If you need the previous, I can go back to it. Anyone need the previous? Everybody get that? Oh, okay. Anyone need it longer? Let me know. I can leave it up there. You need it? Everybody got it? Okay. Then what I'll do is shut this down. And let me mark where we are for next time. Okay. I don't think this is hooked up, so I don't think I need it anyway. All right. For the lab today, the title is Properties of Common Minerals. If you recall in Chapter 17, there was a whole section that was called this. Okay? Now, remember what minerals are? They're the building blocks for rocks. Okay? Minerals are the individual crystalline type objects that are very characteristic of their type, and multiple ones of these go together to make a rock. Now, once I get y'all started on the lab, I'm going to run down to the old physics lab where I have a collection of rocks. I'm going to bring those up, and Rand, they will make a mess. Do you mind? Okay. Yeah, come on in. You got a copy of the lab, right? Okay. So what we're going to be looking at is minerals now. Okay. A lot of what it says here we're not doing. We're going to do it slightly differently, but we're going to fill out the same thing. Now if you remember back when we talked about this, one of the obvious differences between minerals is the color. But the color is not a particularly good classifier, okay? But I'm going to have you record color. There's another thing called streak. Streak is when you take that mineral and put it over an abrasive material and you grind off fine particles. It's sometimes a different color from what the mineral was to begin with. That makes a very good indicator of what you've got, okay? Then there's hardness, and there's the Mohs hardness scale that's given here. And you can either, when it asks for it, you can either put the number down, you can put the name down, either one when it comes time to record the hardness, okay? Cleavage and fracture sort of go together, okay? So you'll find these in where you're going to be looking as a slash, cleavage slash fracture, and you'll actually see that printed that way on the table you'll be filling out, okay? That's where how well the mineral breaks in the sheet or whether it breaks into pieces, fractures. Luster, okay? Luster tells about the surface sheen, and there's various names for luster, okay? Density is, to me, the most important one, and there is no column for density on your table. So on your table, if you flip over to pages 332 and 333, you see that last column that says Other. Wipe out other and put density. D-E-N-S-I-T-Y. That's going to go in your other column. Understood? Okay. And you'll see in those columns, the first column is color, then it goes luster, not quite the same order as listed before. Streak is next, then hardness, and again you can either put the number from Mohs hardness scale or the reference material, and then cleavage / fracture. Okay? And then other will be what? Density. Okay. Now you'll find one other little thing here. Part B on page 331, once you finish the table, which is on pages 332 and 333, then remember to go back and answer the question. The question here is, was the purpose of the lab accomplished? Why or why not? Your answer to this question should show thoughtful analysis. You got one, didn't you? Yeah. Thoughtful analysis and careful, thorough thinking. A sentence or two will be fine. Okay? Don't make a big deal out of it. Okay. Now, how are you going to find this if we don't have the minerals actually to do it with? Okay? Here's how. I want all of you, if you're on a computer and can log into it, then go to a website called webmineral.com. Okay, I'll write it here on the board if I can get the thing out. Okay, now, don't put an S on minerals. It's webmineral.com. There is another site called webminerals.com. That won't give you as good of information. Okay, so if you can get now, Mr. Armbruster said there's several computers short today, so please get with somebody else that's on a computer, team up, be a pair, and work together. Okay? So if you, once you get on, type in webmineral.com. Okay. Now, actually, there is sort of a shortcut. Let me get it for you, if I can find it. Where's my original? I think I put it in the wrong place. Just a minute. Here we go. Put it in the wrong place. After you type webmineral.com, and by the way, it's HTTP, blah, 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 webmineral.com, if you, this might get you a little closer, /data/ I think the first one on here is calcite, isn't it? Yeah, calcite. I think that'll take you right there. Did everybody find it? And get there? Y'all know how to navigate these places better than I do, so that's what you're looking for, webmineral.com, and I think if you actually do /data/ calcite, it'll take you right to calcite. If it doesn't, go through webmineral.com and just keep looking. Okay. Anyone found it yet? Yay or nay? No. Has anyone found it? Oh, yay. Okay, good. All right. Now, do you see somewhere there near calcite, you see something that says something like physical properties? Okay, and you see a lot of these listed. Color, luster, streak. You see just about everything there. Okay? That's where you get your data. And you fill it in. Now, here's something I want to warn you about. The last time I used this, there were a few of these that were not listed on the webmineral.com. I'm going to hit just a couple I think we're missing. I'm not sure. Almost certain feldspar is not there. Does anyone have an idea why feldspar is not there? It's more of a rock than it is a mineral. It's not really a mineral. Or, said the other way, there's a whole class of minerals that are feldspars. Okay? So, what you need to do for feldspar, if you can't find anything on it, do a search on feldspar, a Google search, any kind of search, and then you'll find some mineral names, such as blah, blah, blah. When you find a mineral that is feldspar, then write that on top of feldspar and then do that mineral if you find it in webmineral.com. Does that make sense? For instance, plagioclase may be there, or orthoclase, or potassium. You may find some other mineral. Feldspar is a class of minerals. I think there's a couple more like that. I'm trying to remember what they are right now. It seems like limonite might be one. Or bauxite. I'm pretty sure bauxite is one. If you can't find it in the table, do a search on it, find the mineral that's in that, and then write that above it and do the data collection on that. Okay. Are there still some people who haven't found the website? Or the location on the website? Has everybody got it? Anyone not have it? Okay? What I'm going to do while y'all are working on that, and remember, if you find one you can't find on the table, do a search on it, get a more specific mineral name, write that above it, and then do the one that you get there. I'm going to run down to the lab and pick up the samples, and I'll bring them up so you can see some of these minerals you're looking at. I'll be right back. y'all are looking at minerals. Most of what I'm going to put out here are rocks, okay? But rocks, of course, are made up of minerals. These two I put here are both samples of sandstone. How you can tell? Rub them, and you feel the coarse grittiness of sand. That's sandstone. Okay? My bags are falling apart. Okay. Have you ever heard of something called a geode? Yes.
So, what do you have to write for you?
Okay.
Can it begin or not?
Yeah, you're supposed to be beginning. Yeah. Okay. 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 Yeah. Okay. Yeah. Well, you don't have to put it all. Just put some of this and then do a slash, just like you have a slash here, and fracture. Yeah. So do cleavage slash fracture, just like it is at the top. Write something about cleavage and then something about fracture. Some of them may not have cleavage, and some of them may not say anything about fracture. So put those.
What about for other?
What?
Density.
Density. Okay. Have any of you ever heard of a geode? Okay. What does this look like? Just a rock, right? Sort of an egg-shaped rock, but just a rock. But someone broke it, and when it broke, look at what's inside. You see layers. This was a prime example of some sort of chemical reaction going on that collected and differentiated different parts of this rock. And I have some other samples of a geode that has been sliced. This is actually the rock from which a geode came. Okay? They're very fragile, and this one over the years has broken many times over. This is a much prettier one than that one, but this is a sliced geode. Look at the beauty of that. Okay? And they actually sliced it and polished it. So these came from geodes. Some sort of chemical differentiation going on there. I have several different pieces, like I said, that do fracture easily. Now this, I'm not absolutely certain, but almost, my guess is this may be a piece of slate. Remember we said foliated? This has definitely got foliation to it. It came off in sheets. And this probably could have made it into, if it had been a bigger chunk, into a shingle, for instance. Have all of you started with calcite? Okay. If you read that and maybe even saw some pictures of it, I had a student in this class many years ago, young guy, big guy. He was a miner, okay? He actually worked in the coal mines. And he brought me this sample of calcite. evidently calcite forms near where coal forms. And if you look at this, you see these big, bright, distinct faces of the crystals. Okay? And you'll see calcite has very definite cleavage. You can see the cleavage here. Okay? So I'll put this one here. That's calcite. Now I have several smaller pieces of that same material. I'm trying to keep them from making a bigger mess as they can make.
Mr. Ballard,
Yes.
for mine, it took me to this one. So do you want me to just change that on here?
Yes, that's perfectly fine. That's right. Yeah. I think pronounced your type. Rather strange name. But he brought me several pieces of, you can see coal on one end and the beautiful crystals of calcite on the other side. And I'll put some of the smaller pieces of those crystals out so you can actually handle almost individual crystals. I've got many smaller crystals, and I'm not going to get them all out. Now, I said this was sandstone. Can anyone remember what sandstone is, what type of rock it is? It's sedimentary. And it's a clastic sedimentary, meaning it's made up of particles, not chemicals. Yeah. Okay. I think Michaela found that goethite is another name or one of the classes of limonite. So if you want to try goethite, see what you get there. Goethite, I believe it was his name. Goethite. Now, when my wife and I were redoing or having our kitchen redone, we got the limestone the marble from right down here in Vassar. A really neat place. Had lots and lots of samples, and the guy said had pieces lying all over. I said, "Can I use some of those?" He said, "Sure." So he gave me several to bring to class. This is a sample of granite. Not much biotite in this. You see a little bit specks of black and things, but largely quartz. And you can see pretty large crystal sizes. You can definitely see the crystals there. This is a white granite from Kashmir. It's called Kashmir. It's from India and Kashmir. So there's some writing on the back, so I'll leave it up like that so you can see. Now, I haven't ever had anyone tell me what this is exactly. It's called travertine. And my guess is some sort of an ingrate in between limestone and marble. Not quite as metamorphosized as marble, but it looks like it was one time something like limestone. So I think this is a very advanced limestone. I think that's what travertine is. I don't know for sure. Not mentioned in the books. Here's another piece of marble. This one's from Turkey. It's a cream-colored marble. Okay? This is Indiana limestone. Okay? That is a chemical sedimentary rock, not plastic. The sandstone is plastic. This is chemical sediments. Okay? Recrystallized out of solution. Here's another piece of marble. This is called Calcutta Gold, but it's in Italy, not Calcutta. Okay, very pretty piece of marble there. Now, I have my doubts about this one, but they call it granite. Now, why I have doubts about it, it's awfully dark for granite. But it's definitely large crystal sizes. You can see as you look at that, big old crystals in this, so that fits, but it's a very, very dark colored granite. Okay? So that might be moving towards some of the other things that, if you remember that table they had, there were other darker forms than granite. Now this is a rock, but it's a really pretty rock, very pink in color, and if I'm not mistaken, this is pink quartz. Now it's not pure quartz, it's rock, it has other impurities in it, but some of the crystals look a lot like quartz crystals, so I'm guessing this is mostly quartz. And again, this is more white quartz, and you can see some of the individual crystals in there, sort of that hexagonal structure to them that you see in quartz crystal. So I think this is a different kind of crystal. You notice color is not the good indicator here. These are probably very, very similar crystal rock. One's pink, one's white. So color is not the great indicator. Here's another piece of granite. This is called brown granite. Not nearly as brown as some of that is, but it definitely has large crystal sizes, more biotite and feldspars in this than you saw in this first piece of granite. Now here's another piece of sandstone. And this sandstone, as compared to this one, of course the color's a little different. But if you feel on them, you feel the same roughness of sand. But don't rub on this too much, because this one starts coming off in your hands. So either this one had better compaction and or cementation. This had not as good of compaction or cementation because particles come loose very, very quickly. But those are both types of plastic sedimentary rock, sandstone. You remember in the book, and we're going to talk about it later, this is a sample of my best guess basalt. Dark color, meaning high iron content. Okay? Very, very fine crystal size, which means it cooled very, very rapidly. Most of the time your basalts come from volcanic activity at the bottom of the ocean. And then when it erupts there, it cools really, really quickly, has very fine crystal structure, very fine texture. And this, I think, is a sample of basalt. We'll talk about basalt more, especially in one of the soon-to-follow labs. Okay, now I kind of made a mess here, so I went to the restroom and wash my hands and bring back some paper towels to clean that up.
I'll just pick the first. Yeah. Thanks.
Do go out the door. Don't close it because it locks from the outside. I didn't realize that. Everybody doing okay? No problems? Okay. I think I said this early in the class, but in case I didn't, let me say it now. A bunch of people have not turned in even the first lab or second lab or third lab. Well, third lab you're still working on. So please try to get these labs in, and several of you are also behind on some tests. So please try to get the tests caught up so I can get rid of some of this stuff, okay? I don't want to carry all this around forever. If it's okay, I'm going to shut down the recorder for now, but I'll bring it back up if there are questions.